Go.
Hi, I'm Chloe Garza, and my group is here to talk about electrical design and wiring. And the members are,
Hello, my name is Grant Ozerchuk.
Hello, my name is Austin Worthy.
Hello, my name is Darren Chen.
and now let's begin. So the National Electrical Code is prepared by the Fire Protection Association. And really what they do is just ensure sets and rules for buildings to be up to code to ensure that there's no fire started by electrical causes. And it's a method of connection to make sure that the electrical power and the installation of how it is installed works properly. And so you can find the National Electrical Code in every single building, residential or commercial, as a guideline of how to connect appliances, how to connect computers, how to really design your house or your business to make sure that there's optimal electrical flow to make sure that fires don't ensue. And here we have the most common types of wires that are found for residential use. As you can see, the common are single conductor wires, and these are protected by metal or plastic sheathing. And these are going to be your more white wires that you see here on this slide. They're the middle ones. And next we have the solid core wire, which produces the best connections, but it's a little bit harder. And those are the black wire that you see, because it's not as malleable as the other wires. So it's a little harder to run through conduits. And another common wire that you see in residential use is a multi-conductor cable wire. And those are going to be the wires that have the different types of colored cable inside of it. And what that is the colors allow the installation process to become a little bit easier because they are specified to make sure that connection errors do not ensue. And here we have just different types of circuits. So we have dedicated appliance circuits, and these are going to be behind your washer and your dryer appliances. They're also going to be sometimes behind your computer desktops or just big electrical appliances. And they really run the power circuit to make sure that it's flowing correctly, to make sure that the washer stops and completes the cycle. Next, we have the lighting circuits, and these are going to be found in your outside lighting, in your backdoor patio and restaurants and the outdoors as well. The lighting circuits also control how your lights actually works in your living room. If you have one circuit that controls all of the lighting, or if you have multiple circuits that control different parts of the lighting. And next we have outlet circuits, and these are going to be the circuits that you find on the side of the house that lets generators be plugged in, that lets other type of heavy machinery be able to be used in the house. And next we have room circuits, and this is just going to depend on how your home is actually wired. As these new constructions ensue, you are seeing more often room circuits that control a whole entire house from an app, versus like before where you had multiple room circuits to control each room, instead of how you see now that it's multi-functional with just one switch. And some new circuit board technology is developed by Caltech University, where they actually took DNA structures, just tiny molecular structures found in our DNA, and they've begun to construct them into tiny nanostructures to be used as parts of a circuit board. And that is pretty amazing, just the innovation that you're seeing from our own self, that we can be part of a circuit board that can control a computer. So that's pretty cool.
All right. Hello. Once again, my name is Grant Ozerchuk, and I will be discussing system selection and typical equipment ratings, three-phase versus single-phase wiring, common voltage ratings, coordination with other design decisions, and then preparation of electrical plans and specifications. So first off, wait, go back. I guess we're just gonna edit this out.
My bad.
There you go. All right. First off, with system selection and typical equipment ratings. All right. In power distribution systems, commonly used in buildings include limitations. So the designer must weigh various factors before making a final selection. Some of these factors include cost investment, cost of maintenance, system reliability, serviceability, and then spaceability, and then impact on other building systems. So now we're getting into three-phase versus single-phase systems. So basically what this is single phase is basically just less power, and it's a two-wire system, while three-phase is more powerful and it contains either 3 or 4 wiring systems. Basically, when it comes to three-phase versus single-phase, it matters on load analysis. So basically the electrical power systems are selected to complement the load characteristics. So for example, if the loads in a building are predominantly 120 volt single phase, then the system should be either 120 to 240 volts single phase. And then one advantage of the three phase is in a 4-wire system, it allows a common neutral wire to serve up to 3 single phases load. But also the disadvantage to the 3-phase is that it can easily overheat with the increase of inductive loads. So like, for example, computers in an office, if you're in there and they're using a 3-phase, they could easily overheat and burn up. So now we're moving on to common voltage ratings. So in an electrical power system for a large building, basically this can be a combination of a single phase and 3-phase. It'll be a low voltage system, and it'll be supplied by 1 or more high voltage systems. Now with common voltage ratings in the smaller buildings, it's going to be more of a single power system. It is desirable to separate the large power load from the lighting and appliances loads to minimize voltage fluctuation. Still on common voltage ratings. So basically in these buildings, the following equipment is going to affect the selection of the system during the preliminary design period. So when it comes to either elevators or food service equipment, and then mechanical equipment, and then also you have your household appliances. And now moving on to our coordination with other design decisions. So basically this is just the interfacing of a building system. This is how your mechanical and electrical side flows throughout the building. So in this image we have over here, you can see how complicated the interfacing of the building system is. I mean, you have everything from your switchboard to your circuit breaker, how they open and how they close. And then now you have your coordination with other design decisions. This is basically your accessibility, which is all the equipment and devices must be accessible for inspection, service, and replacement. Safety, this is your electrical equipment, and electrical equipment is hazardous. So clearance must be provided on all sides that require access. And then you have common access space. This is to minimize the loss of useful building space. And then you have integration of electrical and structural. So basically this is just the spacing is either under the floor system or is it a cellular floor system, and You gotta have access to both floor systems. And then you have your preparation of electrical plans and specifications. So basically, right here to the image on the right, these are your basic graphic symbols that are used to indicate various aspects of electrical designs. So whether it's including equipment, devices, wiring, and raceways. So at the top, you see we have a couple wiring, which is a couple wiring graphic symbols, which show that it's either above the ceiling or whether it's below the floor or the wiring is exposed. You have your switchboards, your transformers, fuses, plugs, circuit breakers, thermostat, and your motor. And then you have your preparation of electrical plans and specifications. Electrical plans consist of the following. There are floor plans, which are basically in a floor plan, the electrical devices and equipment are basically just on an architectural background. Then you have the schematic diagram, which is also called an elementary diagram. This illustrates the circulatory of a system. And then you have your connection diagram, which is also called the winding diagram. This shows the connections between winding terminals and equipment. Your one line diagram, this shows the relationship among major equipment. And then your riser diagram. This expresses the physical relationship between different pieces of equipment. And then last, you have your specifications. And this is the image to the right. This is basically just a written portion of a design document that are used to supplement the drawing. This is kind of like your table of contents.
All right. My name is Darren Chen. I will be talking about power wire systems designs in a building. What is a power wire design? A power wire design is basically a 2D blueprint of all of the electrical wiring that goes into the building. Why is this important? Because it will tell you how much financial money you need to spend on the building. It gives you a time scale of how much time it would take to wire the whole building. Then it will also prevent injuries because the diagram will tell you specific places that certain wires needs to be. Or else it needs to be also applied to certain codes. What is a low voltage wire system? Low voltage is basically anything under 50 volts or less is considered low voltage. Some examples are your network security systems and cabling. There are also the wall outlets in your house is also considered low voltage, but that is a small area because certain appliances needs high voltage, such as your washer machine, dryer, dishwasher, and oven, and etc. But other than that, every other appliance is considered low voltage. Here's are some diagrams of a wire system that a electrician would probably use to design a house. For the picture on the left, it would be all your lights, how they're connected in a building. How all of the lights are connected on your first floor, then how all of your lights are connected on your second floor. Then on the right, you see a picture of switches and outlets, how they all connect to each other, how it will power a house. So here are some low voltage wiring usages. Your house phone will be considered low wiring voltage. Then your internet, cable, Ethernet, and security systems will also be considered low voltage wiring.
Hello, my name is Austin Worthy, and I will be talking about electrical design procedures, analyzing building needs, and determination of electrical loads. So there are 5 basic steps in electrical system design. First, we're going to talk about analyzing your building needs. You need to know what type of material, the type of manpower, the type of equipment. Determine your electrical loads, whether you want it to be inductive or resistive. Select your electrical systems. Most homes have a 3-wire system. Coordinate with other design decisions and prepare electrical plans and specifications. And some of these steps might be bypassed just to keep the project on course. Next, we're going to talk about analyzing your building needs. The first step in electrical system design is to identify the needs of the building established by the architectural program. Here are 9 major factors affecting electrical system. First, it's your occupation factor. What type of building occupancy? The cost factor. What type of budget do they have for the building? The architectural factor, which goes by the size, the building environment systems, whether it is heated or cooled, the illumination criteria, the lighting level, or the types of lighting sources. Other mechanical systems, building equipment such as food prep and recreational equipment. Auxiliary systems such as a clock, fire alarm radio, TVs, and space capacity. There should be 25% spare capacity provided at the power main. Next, we're going to talk about determination of electrical loads. The need for electrical power in buildings rose dramatically through the 1980s into the 1990s because the increase in the personal use of computers, telephones, printers, fax, and copy machines. First, we're going to talk about lighting power, which is usually coordinated by the architect, light designer, or the electrical engineer. Mechanical equipment, building equipment, which includes vertical transportation, such as escalators and elevators. Auxiliary systems, they usually don't require a large power capacity. Surveyor rooms, convenience power, which is like they power provided for plug-in equipment such as corded drills and jackhammers. And lastly, we're going to talk about connected and demand loads. Connected loads are algebraic sums of all electrical loads connected to the system, and the demand load of a power system indicates the next load that will be used at the same time for each load. These are our references, and we thank you for your time today. And if you have any further questions, please do not hesitate to email.